Okay, everybody, we're going to get started. Hope your day's been a good one. This is I think our first class since we had daylight saving time. And out my window, geez, it really feels like springtime. It's so bright here. The plan tonight is we're going to be working through ideas within Chapter 8. I think we'll finish up Chapter 8 next class period, but we're going to get a big chunk of it done this evening. I mentioned there as far as resources, you're going to be consulting a periodic table. So if you've got something like that you can look at along the way, that'll be helpful. And you're also going to be making sketches. You're going to be making some Lewis structures and following along the process. And so being able to write those along the way, I think that'll really help you. So last time we began Chapter 8 by looking at some ideas of ionic bonding. We want to be familiar with the energetics corresponding to the formation of these ionic bonds. So our big idea here is that when we have these cations and anions coming together, the energetics for those, well, we have to be making the cations and the anions, and then we have to consider what does it mean to have them all come together. So as far as the different learning outcomes or what we're up to, last time we were looking at aspects of the Born-Haber cycle. That was being used to describe these energetics. Here was an image that we had last time. So we thought through what did an image like this describe, and it was really giving us a pathway where way at the bottom we see the ionic compound, and as we follow through our trajectory, you notice way up near the top we're getting to have the cations and the anions, and they're at a much higher potential energy, a much higher enthalpy than the corresponding solid was. And the reason the formation is exothermic is we have this coming together of all of the cations and anions to form this extended solid, this extended lattice in 3 dimensions. And the energy corresponding to that, we were thinking about it in terms of what we call the lattice energy. But what really is the lattice energy? How can we begin to quantify all of that coming together? So I want to begin class by looking at that. We want to be able to understand what the lattice energy is. And the classic exam question on this is to be able to evaluate different ionic compounds and rank them in terms of their lattice energy. So let's see what contributes then to the lattice energy. So our learning objective, we want to be able to arrange compounds in order based on their lattice energy. And we have 2 variables to consider: the charges for the ions and their sizes. Here's a description, a calculation that shows how these variables come together. You have the charges of the cations being multiplied by the charges of the anion. So just for an example, it might be +1 and -1, or +2 and -2. We have a positive cation and negative anion. So if one of those is positive, one of those is negative, notice it will give a potential energy value of negative. One is positive, one's negative. The product of that is negative. And that's how we made sense of the potential energy, or I've been trying to have us make sense of the potential energy. Our reference value of 0 is when they're far apart, and as these cations and anions are coming together, they're moving to a lower potential energy, which becomes more and more negative. So this particular attraction, we thought about it initially in terms of like 2 magnets. 2 magnets, we defined the potential energy as 0 when they were far apart, and as we had them in our hands and they moved closer and closer together, they were moving to a lower and lower potential energy. Now, the particular attraction, though, they had, think about those 2 magnets. I think the attraction was greatest when your hands would have been right close together. So this attraction is going to be greater when the charges are larger and when the charges are closer together. This will be what describes a larger lattice energy. 2 different variables: the charge and how close they can get together. And out of these 2, the charge is going to be the more important one. Let's work through and see how this comes together. So at the top right here, I've got 1, 2, 3, 4, 5, 6 different ionic compounds. All of these include metals, nonmetals. These are all metal cations, nonmetal anions. So our task here is we want to rank these in terms of lattice energy. Out of these 1, 2, 3, 4, 5, 6 different compounds, which has the highest lattice energy and which has the smallest. Rankings like this, I mean, we see these all the time in mastering chemistry. This is the exam format that I'd expect. So if I'm thinking about which ones have the highest lattice energy, the first thing I'm going to look for is the charges. The larger the charges, the higher the lattice energy. And just as an example, within this first one, lithium fluoride, if I look at my periodic table, lithium is +1, fluoride's -1. So the charges here are +1 and -1. Just as another comparison, let me say I'm looking at calcium oxide. Calcium's an alkaline earth that's in the +2 column. Oxide would be in the -2 column. So right there, I know calcium oxide has a larger lattice energy than the lithium fluoride. I'm looking at the charges first. So take a second, see if you can find these on your periodic table. Which ones do you think have the largest lattice energy? Which has the smallest? And just like in mastering, if they overlap, try to put them both in the same spot. So take a second, do your ranking in terms of charges first. So here's how I would go about that. I think the ones that are +1 and -1 were the lithium fluoride and the sodium iodide. Magnesium oxide, calcium oxide, those were +2 and -2. This one, scandium nitride. Scandium, that's not one that I've memorized on the periodic table or something, but I know that nitrogen is 3-, the nitride anion. So it must be +3 and -3. Those are the greatest charges. Notice where I put this one that was like an in-between. This is +2, -1, -1. So I'm putting that in between the ones that are +1, -1, and +2, -2. So this one that is sort of a combination, I'm putting that in between on the rankings. So right away, we've made a lot of progress. We've been able to come up with a pretty good analysis for the lattice energy simply by using the periodic table and identifying the charges. But now we've got a couple that are tied. We want to break those ties. So the second variable we're going to look at is size. The smaller the size for the cation and the anion, the closer they can get together and the larger the lattice energy for that. The smaller the size means that positive and negative charges can get closer together, and that leads to a greater attraction. So how do I decide if they're smaller or not? I'm thinking back to my periodic trends that I had back in chapter 7. Magnesium is smaller than calcium. Magnesium 2+ is smaller than calcium 2+. So I'm going to put the magnesium oxide and make that little bit closer, higher lattice energy. And that was the tiebreaker that was based on size. Smaller size leads to greater attraction, which means a larger lattice energy. Give it a try. See if you can break this tie right here. Lithium fluoride, sodium iodide. See if you can put the ranking together there. Use the periodic table to do that. I see a question there as far as, am I looking at molar mass? I'm not looking at mass whatsoever. When I'm thinking size here, I'm thinking back to the size for the atoms and ions that we had in chapter 7. I'm not thinking about what the mass adds up to. I'm thinking of the periodic trends from chapter 7. Good question on that. So my tiebreaker within these, I am going to put lithium fluoride as being smaller, closer together than the sodium iodide. How about, let's compare the cations first. Lithium is smaller than sodium. And how about the anions? Fluoride is much smaller than iodide. Because they're smaller, they can get closer together, and that leads to a greater attraction, which means a higher lattice energy. So notice within this ranking scheme right here, we had a really clear system that we can always use for lattice energy. The clear system that will always work, we will first use the periodic table to assign charges. Higher charges means higher lattice energy. And then if we have tiebreakers, if we have to do that, we will then use size as the tiebreaker. When we look at the corresponding, these are the experimental values. it matches our ranking perfectly. Notice how the +3 and -3, such a huge lattice energy. +1 and -1, much, much smaller. This explains why in our Born-Haber cycle, when I kept saying, oh, the lattice energy is the key. The lattice energy is the key. That's the one that makes the entire process exothermic. It is going to be really tough to get nitrogen 3-. I got to add 1, 2, 3 electrons to nitrogen. That's not going to be favorable. But notice once I get there, I can then have this huge lattice energy, which makes the entire thing go to a lower potential energy. So this idea here of rankings involving lattice energy, really common exam question. So I list here a couple end of chapter questions. This one right here, 8.24b. This is really typical of what we see on exams. It says, arrange the following substances here based on their expected lattice energy. This we would use exactly the strategy that I just mentioned. We'll first use a periodic table and look and assign them based on charge. And if we have any tiebreakers, we would then look to size. I'll say last time on this topic, I am absolutely sure you're going to have an exam question involving ranking for lattice energy. So that was our discussion there of ionic bonding, looking at the energetics for those. All of the rest of the chapter is not on ionic bonding, but on aspects of Lewis structures. With an ionic bond, we are interested in the transfer of an electron to make cations and anions, and then how they all came together. All of the rest of the chapter here, they're involved with this process of drawing Lewis structures. When I looked within the comments and questions people had in perusal, outstanding job working through these ideas. I'm so impressed with how you've been able to use that as a space to help out each other, get your own questions answered. I'm really impressed with the contributions that you're having in that space on this topic. One thing that I was seeing there was, well, when we're looking at Lewis structures, is that something that we use for ionic compounds? It really isn't. Okay, in an ionic compound, I don't really have a distinct molecule because I have this whole extended array of pluses and minuses, pluses and minuses. When I'm looking at these distinct molecules, that's when a Lewis structure is really helpful. So let's see now, when I say we're going to do some sketches, we're going to work through some different ideas and have you practice drawing Lewis structures. So I think within this evening, we're going to look a little bit at 8.1. And then we'll look at the ideas in 8.3, 4, and 5 and practice drawing Lewis structures. So the first idea here in 8.1, these Lewis symbols in what's called the octet rule, they're a very simple way to describe the bonding between some atoms. We are going to look at more complex ways, but this is a simple way to get it started. So in 8.1, we want to be able to draw Lewis dot symbols. And in order to do that, we need to know the number of valence electrons. So a quick refresher within there, number of valence electrons, we can use a periodic table to get that really easily. Just by looking at the column that they're in. 1, 2, 3, 4, 5, 6, 7, 8. As I move left to right, those are the number of valence electrons I have. So within this image from the book right there, it shows how you have the different electron configurations. Those are consistent with what I just mentioned at the periodic table. Now, the particular Lewis symbols are shown below that. So our strategy for this is we're going to add these dots around the central atom. We add them individually until we get up to 4, and then we start to pair them up. So if I'm adding around chlorine, I've got a total of 7 electrons to add. There's 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. That would be one way that I could draw it. When I say one way, this would be an equivalent Lewis dot symbol. The orientation doesn't matter. Doesn't matter if you've got them up, left, right. If you draw one like this, however, that's not correct because it doesn't have the correct number of valence electrons. So our plan for these, we're going to put them in independently until we reach 4, and then we begin to pair them up. It also tells me that there's going to be patterns for each of the columns. Carbon and silicon will both have 4 unpaired dots. Oxygen, sulfur, I see the same pattern as I look down that column because they have the same number of valence electrons. So the Lewis dot symbols here, it's going to communicate the number of valence electrons. It will show me the number of lone pair electrons. And by lone pair, I'm talking about these ones that are in sets of 2 that are paired up. They're typically not involved in bonding. When I have unpaired electrons, that electron could be involved in bonding. So right away, this gives me a pretty good clue. The lone pair ones are not involved, but the unpaired electrons are. And when I say a pretty good clue, I can look back at these columns in the periodic table. I see right away that carbon here, it usually forms 4 bonds when it's in molecules. Chlorine, it usually forms 1 bond. How about nitrogen? I see 2 that are paired up and then unpaired, unpaired, unpaired. Nitrogen will usually form 3 bonds. So one skill that's really useful is being able to look at the placement on the periodic table and just get a head start. How many bonds does that particular element usually form? It won't always be the case, but how much does it usually form? The periodic table helps us on that. So then if we look, how do we now take these symbols that we have for the atoms and begin to form molecules out of these? So the big idea here in 8.3, we're going to see in these molecular substances, atoms are often going to form bonds by sharing the electrons. So what we want to be able to do is we want to be able to draw and interpret Lewis structures and think about the bonds that are forming. So in this one, hydrogen with another hydrogen atom, you see both of these have an unpaired electron that can now be shared and found between both of the atoms. Instead of drawing both of those dots representing 2 electrons, that's what the single line represents. A single line represents 2 electrons that are being shared between those atoms. Now, let's not forget that we still have nuclei there. We still have protons. These electrons, they're not being found like in this line, right? They're not somehow in this rigid line between the 2. Where are the electrons? The electrons are found between the 2 atoms. They're being found within this space here. They're being found when I say shared. A given electron, it could be attracted to one nucleus and the other nucleus at the same time. In a sense, the electrons now, they're like the glue. If they are found between the 2 nuclei, they could be attracted to both of them and leading to a net attraction. So when I'm thinking, where are the electrons before I put them in atomic orbitals? Now I'm beginning to think, okay, if those electrons are found between the 2 nuclei, I could have opposite charges attracting both of them. That could be the glue that's causing them to stick together. So conceptually, I'm starting to think, how does sharing the electrons lead to a bond? Sharing of the electrons is giving me a net attraction that will be bringing those nuclei together. So whether I'm thinking about it here in terms of the probability of finding the electron somewhere, or being shared by showing these 2 dots or these lines, conceptually, this is what I'm trying to bring together. So here I show within the sharing of electrons, how if you have 2 electrons, 2 dots coming together, that could lead to a bond between the 2. I show how that's taking place in H2 and in CO2. In both cases, those shared electrons, that's what's being represented by the single line. So now we have a pattern that's going to be useful for us. The pattern is called the octet rule. The octet rule is telling us that chemists found when they're looking at it this way, for some elements, and I'll tell you which ones, but for some elements, the bonded atoms, they seem to follow this pattern, where if we counted up the number of electrons around a given atom, it added up to 8. Or in the case of hydrogen, hydrogen's easy. All hydrogen is ever going to do is form a single bond. That's all hydrogen is ever going to do for us. If we look within the chlorine one, notice it had 2, 4, 6 that were lone pairs and 1 that was unpaired that could then lead to a single bond. When we brought those together though, notice how the math works. For this chlorine atom, I see 2, 4, 6, 8 electrons around it if I'm counting the shared ones as being accounted for that atom on the left. And the same thing for the atom on the right. That would also get me to 8 as I'm counting them shared up that way. That's what the octet rule is. The octet rule is this pattern of how I'm adding up the ones that are either on the atom or shared, getting to 8, and seeing that that describes many times what happens with the bonding. Now, this right now, it's going to be useful for us. The octet rule is going to be useful to help us draw some Lewis structures. It doesn't really explain what's going on with bonding, though. I mean, my electrons, they don't know how to count up to 8. They don't say, oh, okay, good, I'm at 7, now I'm at 8. No, there must be other things going on there. But I'm just saying right now, this is a useful pattern that will allow us to use the periodic table to begin to draw many different molecules and to consider the bonding. Later on in chapter 9, we're going to go beyond this a little bit, but this is a really important head start for us. So quick thought here, when is the octet rule useful? Well, I looked at these different Lewis dot symbols. So you notice my noble gases, I've got those that are filled up with these groups of 8 already. I see that I have 1 unpaired, 2 unpaired, 3 unpaired. So these would be the Lewis dot symbols. When does the octet rule work? Well, in a way, it's really not helpful for my cations. Those are going to be found as metals or ionic bonding. It's not really going to be found with my noble gases because those don't really form bonds. It's not going to be strictly followed for these because we're going to see these go beyond the octet rule. We see boron does not reach an octet. When is the octet rule useful? It's really useful for the ones that I show right here. For hydrogen, I'm going to expect single bonds only. And then the octet rule, when does it work? It will be great for carbon, nitrogen, oxygen, and fluorine. It will be great for those. And we might think, well, look, you've eliminated a lot of the periodic table. But you know what? All of organic chemistry, carbon, nitrogen, oxygen, these are the elements crucial to life, okay? In your bio class, almost everything you look at is carbon, nitrogen, oxygen. So I'm not dismissing the octet rule. I'm just saying this is where we want it to recognize that it is really useful for carbon, nitrogen, and oxygen. And with hydrogen, only a single bond. Something like chlorine I'm leaving out because we're going to see that often will also exceed an octet. These are the ones, though, that I'm really confident it will work for. Okay, so I'm going to add a new idea for us here. So in 8.4, it brings up this idea of bond polarity, electronegativity, and the dipole moment. This was not in the pre-class video. The big idea here is that when these bonded atoms come together, if they have different what are called electronegativity values, the electrons will not be shared equally. So what do we do with this? What is the learning outcome? We want to know what different electronegativity values are, and we're going to use that to describe bonds as being ionic, polar covalent, or nonpolar. So let's go back to the one that we had just a moment ago. 2 chlorine atoms come together. The 2 chlorine atoms come together, and those 2 electrons are being shared between both of the chlorine atoms. I would say when both of the atoms are the same, they're both chlorine, there's no reason for the electron to be predominantly on one atom versus the other. I think they're going to be pretty equally shared between both of them because they are the same atoms on each side. But what if I have different atoms? Soon as I have different atoms, any 2 atoms that are no longer identical to each other, when they're forming the bond, we're going to see that the electron is not equally shared right between both of them. The electron density, where the electron is more likely to be found, is on one of the atoms more than the other. That idea of saying it's on one of the atoms more than the other, that's what the electronegativity tells us. Electronegativity is the ability of an atom to attract electrons to itself when it is part here of a compound. So when an atom is bonded to other atoms, how much of an attraction does that atom have for the electrons that are within the molecule? That's what the electronegativity is telling me. So here I give different electronegativity values. You do not have to memorize the values at all, but we do need to know what the trend is. So when I look within this one, by far the most electronegative is fluorine. I'm not looking at the noble gases because they're not really found in molecules. So my most electronegative is fluorine. The next most electronegative are the two immediately to its left and immediately below it. So if you got a periodic table right now, add this notation to it. Add this notation that shows where the most electronegative is. And then show the next most, nitrogen and oxygen and chlorine and bromine. There's a clear trend of electronegativity. Electronegativity increases as I'm moving on the periodic table towards fluorine. Up and to the right towards fluorine, that is the most electronegative. One other feature I want to add on here, which is an important one, is I say note the position of hydrogen. Hydrogen is a non-metal. Its electronegativity on this scale, 2.2, puts it just between boron and carbon. So if you've got a periodic table right now, designate where hydrogen is found. Hydrogen is found between boron and carbon. So now we have a sense of this electronegativity scale. Let me show you how it plays out a little bit. So I'm going to represent and look at differences here of electronegativity and see what does that mean in terms of where the electrons are found. So this is within a PhET sim that I'm going to share with you. Let me give you a couple details, a preview on this. So first of all, within the sim, I'm able to change the electronegativity of the atoms, A and B. I'm able to describe the bond as being covalent or ionic, or somewhere in between. I'm able to look at this representation and it's color-coded in different ways. I see an arrow pointed in one direction. I see these small Greek letters. Let's see if we can begin to make sense of these different representations and how they connect to electronegativity. So I'm going to manipulate this a little bit. So to begin with, I'm going to turn on a few different features in the sim. Okay, so what I've just turned on right there, bond dipole, that corresponds to this arrow. Partial charges, that corresponds to that small sigma minus and sigma plus. Bond character, that's this description here between covalent and ionic. And electrostatic potential is showing me this side is more negative and this side is more positive. So let me bring together a few of these different representations for us. First of all, notice the electronegativity. Atom B is more electronegative than atom A. Atom B is attracting the electrons more than atom A. So if I look up within here, the one that is attracting the electrons more, notice it's putting the negative region on that side. It is partially negative. It's not completely +1 or -1 like you'd have with a cation or an anion, but it is partially negative because it is more electronegative. The arrow here, the arrow is pointing to the more negative region of that bond. And it's not just pointing, it sort of has this X on the left-hand side. The way I think about it is it's as if there's a plus sign on that side and it's pointing to the more negative. So there's different representations that are communicating what these differences in electronegativity tell you. So what I'm going to do next is I'm going to make atom B more electronegative. Let's keep track of what's happening within the sim then. See if you can spot changes. Okay, I'm going to stop it there. So what changes did I see? Well, first of all, these partial charges, they're trying to say this is even more negative. This is even more positive. It's got these cool colors, the red and the blue, to show that you've got even more differences in charge. They're trying to show that that bond dipole is even more pronounced. Also notice here in terms of the bond character, I am at an extreme difference in electronegativity. Atom B is very negative compared to atom A. And it is describing that as being more and more ionic. It's more and more like we've got a cation and an anion. If I reset to where whoops, sorry about that. If I reset back to where I was, notice how it's moving away from the ionic part. This description right here, in terms of the bond character, ionic bond is when we have cations and anions. It is completely covalent when the electronegativity values are the same. When it is somewhere in between, we call that polar covalent. So we have ionic compounds, we have ones that are completely covalent. In between, we have ones that are called polar covalent. What I'd like you to do is make a prediction here. I'm going to take the electronegativity for atom A. Right now, it's really small. I'm going to increase it. I'm going to move the dial up. Make a prediction. See if you can predict what's going to happen within this representation. Notice what happened along the way. I double back to that spot. Notice there was a point where the electronegativity was equal on both of the atoms. It's calling that now covalent. I don't see any partial charges. There is no bond dipole. But if I were to make that even more electronegative, now I'm back to having a polar covalent. I see the partial charges emerge. And I've got a partial negative and a partial positive. This right here, this is where we ended up at the end of that simulation. I have two different electronegativities for the different atoms. I've got one then that is the more electronegative that has a partially negative sign on it. The less one, that's the partially positive. And there's a bond dipole that's pointed to the more negative region. So I'd like to give it a try here. Here I show different representations. One of these corresponds to lithium fluoride. One corresponds to F2, and one corresponds to HF. I want you to try to match these up. Which one do you think is F2? Which one do you think is HF? Which one do you think is LIF? Consider where they are on the periodic table and the type of bond that you'd expect to have present there. See if you can match that up, and then I'll share my work. Here'd be my stab at it. So on the one at the left, I don't see a positive and a negative. That tells me that I have both of the atoms be the same. Now, fluorine, it's very electronegative, but if it's paired up with another fluorine, it's going to be a covalent molecule. This one's best represented in ionic, and this would be somewhere in between. So when I say somewhere in between, we have an ionic compound, which is one extreme, a nonpolar covalent, which is the other. You'll see it called either nonpolar covalent or pure covalent. And in between is a polar covalent one. If I wanted to add representations on that, I think that this would be partially negative on the fluorine side, partially positive on the hydrogen side. One more thought for you on the same topic. If you see this language here, the description, we've just been talking about whether we had a polar molecule or not. Differences in electronegativity giving rise to a polar molecule. That will also be called as having a dipole moment. The symbol for that is mu. So if you see this language or a question that asks about, is it something with a dipole moment? Dipole moment means that it is a polar molecule. So if I'm thinking something like F2, would F2 have a dipole moment? The answer is no. It is not a polar molecule. This idea of whether something is a polar molecule, if it has a positive region and a negative region, that's going to be a really important idea for us that we're going to build up to in chapter 9. Now, one thought within here before I leave that slide, here's our calculation for what gives rise to something have a dipole moment. It has to do with the charges, that's Q, and the distance that they're apart, R. I don't think, I'm sure you're not going to have to do a calculation involving a dipole moment, but this is what gives rise to a dipole moment. A dipole moment would be larger if the charge separation is greater or if those charges are further apart. Qualitatively, that's what gives rise to a larger dipole moment. So here's, I looked at the end of chapter questions. What's typical? How do we typically go about it? This question right here, 8.42, really typical exam question, this format. Arrange the bonds in order of increasing polarity. How do we go about that? We want to think back to our pattern for electronegativity. The closer the two values are together, the more covalent it is. The farther the apart values they are, the more polar it is, the increased polarity. So just to look at an example between two of them, let's say I wanted to compare the polarity of a carbon and fluorine bond or an oxygen and fluorine. I don't need the values listed here to know, oh, fluorine is my most electronegative. The next tier close to that would be the ones immediately left and immediately down. So oxygen and fluorine, they're going to be much closer in electronegativity than carbon and fluorine. That's what I mean of being able to use the periodic table and judge based on their placement in the electronegativity. Is it a more covalent bond or a more polar bond? The one thing that I'll point out that you need to be careful of, remember the placement for hydrogen. It's just to the left there of carbon. Okay, so here's the next one as far as the next skill that we had. First skill I mentioned was rankings involving lattice energy. I'm absolutely certain you got an exam question on that. Next one that we built up to would be talking about bond polarity, and we would use the periodic table for that. Okay, now let's get back to some ideas that were in the pre-class video. So the next one right here, I'm showing how we could now have Lewis structures that will describe some simple molecules. So first thought that's helpful, I show up here at the top right, this was thinking back to the number of bonds that these atoms typically form. That was based on their Lewis dot symbol. Fluorine typically is 1 bond, oxygen 2, nitrogen 3, carbon 4, and hydrogen's back to being just 1. So within this one, the setup within this, just by knowing the number of bonds that they typically form, we can use that information to see how do they fit together to form these molecules. If I look at each of these are all consistent. They all make sense with this simple pattern here for how many bonds that I would expect. In each of these cases, I see hydrogen forming 1. In each of these, I see the oxygen forming 2, nitrogen forming 3, carbon forming 4. This idea here of just a single line, those are representing single bonds. Let's connect this to what we just did a moment ago. If I were to think about the polarity of these bonds, I think the one involving carbon and hydrogen would be the most nonpolar, the most covalent, because hydrogen is right next to carbon within my electronegativity scale. Hydrogen and fluorine, that would be the largest difference. So I'm now trying to connect this description of bond polarity with these different Lewis structures. These are examples of single bonds. If instead of having 2 electrons being shared, if you had a total of 4 between, those lead to double bonds. We have 2 sets of lines. If we have a total of 2, 4, 6 electrons in between, those are triple bonds, 3 sets of lines. When I'm using this notation, single, double, and triple, we'll also see that described as the order of the bond. A single bond is just a bond order of 1. Double bond is 2, triple bond is 3. So this language of, is it a single, double, or triple? What we're really describing there is the bond order. Now, we're going to spend some time looking the rest of the class here at different aspects of Lewis structures. Lewis structure, really important idea in chapter 8 and in chapter 9. It's going to be a tool that we use. We're going to use it in 8.5. We use it again in 8.6, 8.7, and then at the start of chapter 9. So this is a high priority for us. We want to be able to draw Lewis structures, and then we want to be able to evaluate them and say, well, do we think we drew the right one? Because sometimes there's going to be different ways that we can draw these Lewis structures. So we need a way to be able to identify what we think might be the best one. So another new idea for us, one of the ways that we can determine is it a good structure is the octet rule. Another way that we can do it is by calculating what are called formal charges. And I'm going to illustrate those for you in just a second. So my plan here is I want to work through several examples. I want to go through several examples, and we're going to apply that strategy that's listed in the book that will always work for drawing Lewis structures. The ones that I first introduced there, things like NH3, H2O, CH4, I think you're going to be quickly recognizing the correct Lewis structures for those, because we're going to be seeing those quite a bit. There's nothing wrong with quickly recognizing and saying, oh yeah, I know what H2O looks like. That's a great skill. But I want to give you a strategy that's a little bit more complex because it will always work. You don't have to recognize anything with this. You can follow this plan, and this will always lead you to the right Lewis structure. So let's see what the plan is. We have a strategy that we can use, and then we can evaluate it. Let's see if we can practice both. What does it mean to draw the correct Lewis structures and then begin to evaluate them? So the very first step, we're going to add up and determine the total number of valence electrons that we have. We want to have the total number of valence electrons in that particular molecule. We just come up with a total. Now, if it's a cation or an anion, we're going to change that. We would come up with the initial total, and then if it's a cation, that means we've lost an electron somewhere. So we would change our total, decrease it by 1. If it's an anion, we'll just add another 1. Notice it said, do not worry about keeping track of which electrons came from which atoms. Once they're in the molecule, they don't own the electrons anymore. Only the total value is important. This is the first thing to keep in mind. A lot of students freak out and they're like, oh, well, how many does carbon have? We just want to know the total number. That's our first goal. Second goal, we want to be able to make an initial sketch. We want to put an atom in the center and then see how the other ones are connected from there. There's different guidelines that are listed, how oftentimes the formula can help you, but I've just added a new piece of information that wasn't in a pre-class video because I've just introduced, the idea of electronegativity. Generally, the atom that we put in the center is the least electronegative. Carbon is less electronegative than something like fluorine. Carbon is more likely to be found in the center. Let's see if that holds up, but that's a really good clue that will help us out. We're going to make a sketch. where we're going to draw single bonds initially. We're going to complete the octets around the exterior atoms. And then we're going to see what does it mean to complete the octet around the center one. And we might have to shift the electrons around to make that happen. And then we can evaluate it. So let's try it. So here's one that was in the pre-class video, drawing the Lewis structure for CH2O. If I use a periodic table, I can get the total number of valence electrons. Carbon has 4, each hydrogen has 1, oxygen has 6. That gets me a total of 12. When I'm writing these, I usually, once I get that number, I write it down. I write it down when I begin making my sketch, just so I know I have the right number there. The least electronegative within here, I think carbon is a good choice. Because carbon, the one that I put in the center, I don't want to put hydrogen in the center. Hydrogen only forms one bond. There's no way hydrogen can be in the center. I need something that I can bridge off from, make quite a few bonds. Carbon is a great choice for that. So I'm going to draw single bonds throughout. I'm going to complete octets around the outside for the oxygen. Hydrogen's easy. All hydrogen can do is form a single bond. So my hydrogens are already done. I've added then the electrons to complete the octets around the outside. At this point, let's add up how many electrons we have. 2, 4, 6, 8, 10, 12. I'm counting each of the lines as 2. 2, 4, 6, 8, 10, 12. So I've got the right number of valence electrons. The hydrogens look set, but that carbon right there, the carbon's not set. It doesn't have an octet around it. It's only got 2, 4, 6 electrons around it right now. How can I make it an octet? Well, I could switch one of these 2 electrons. I could, these pairs right here, I could shift it in there and make a double bond. When I'm shifting the electrons, when I'm reallocating them, I'm just interested in where do I end up? Where I ended up, each hydrogen forms a single bond. That's what I want to see. This carbon right here, by having a double bond, I see 2, 4, 6, 8 electrons around it. That's an octet. For the oxygen, I see 2, 4, 6, 8 around that. That's an octet. I like this Lewis structure as being one that is consistent with the octet rule. It works great. I think this is the best structure that I could draw. It's consistent with the octet rule. I got this other variable that I can look at, which is a new one, which is called formal charges. Let's show how we evaluate this in terms of formal charges. This is another skill we want to have. This gives me the math for how do I do that. I calculate the formal charge for every atom within the molecule. The formal charge is looking at the number of valence electrons minus half the electrons that are found in bonds minus the ones that are non-bonding. Let me show you how the math works. So for each of the hydrogen atoms, they have 1 valence electron. Carbon has 4 valence electrons, oxygen has 6. Next step is let's subtract half of the number that were found in bonds. For this hydrogen atom, there's 2 electrons here found in bonds. It gets 1 of those. It doesn't have any non-bonding. So the formal charge, if I do the math, 1 minus 1, nothing in non-bonding, ends up being 0 for the hydrogen atom. For the carbon, carbon started with 4. If I were like almost mentally cutting each of those bonds in half, it would have a total of 1, 2, 3, 4 electrons that were involved within bonds. No non-bonding, it ends up being 0 there. Take a second, see if you can calculate for oxygen. What is the formal charge for oxygen in this molecule? So if I'm doing my math here for the oxygen, I see within here, it's got a double bond So it's going to get a half of those 4 electrons. And then I see 1, 2, 3, 4 that are being found for non-bonding. So for my oxygen right there, that's another case where it's ended up having a formal charge of 0. It got half of the ones that were found in the bonding. And then it gets entirely the ones that are here at the non-bonding. So it ends up with a formal charge of 0. So you might ask, well, why are we going through this effort of formal charge? We're going to see in just a second that this is an important skill that we want to be able to have. Another thing I'll point out is the formal charge. If you add up all of the formal charges, it gets you to what the charge is on the molecule or the ion. To me, it's a really good check to make sure I drew the Lewis structure correctly, that I added up the number of valence electrons correctly. I want to make it where, okay, if this is a neutral molecule, the formal charges should add up to 0. And in this case, they did. If we're using the formal charge to evaluate whether a Lewis structure is good, if we can have values at 0, 0 is best. We want to have formal charge values of 0. Now, there might be times when we draw the structures where we can't have them all be 0. If we have to have negative values, we want to put them on the more electronegative atom. And finally, this idea that if you add up all of the formal charges, it adds up to the charge on the molecule or the ion. We're going to practice using formal charges with a couple Lewis structures here. So I've got some examples where we're going to explore them in different ways. This is one that was also within the pre-class video, where the first step, once again, let's add up the total number of valence electrons. My central atom in this case is going to be the phosphorus. I'm going to draw single bonds all around it. I'm going to complete octets around the outside. At this point, I pause and say, how many electrons have I accounted for? I've accounted for 24 electrons. I need to get to 26. I've got to add 2 more electrons somewhere. I already have octets on the outside. I don't have an octet on the phosphorus, so I'm going to add my remaining 2 electrons there. Voila, it works for the octet rule for all of them. What about the formal charges? This is my calculation for the formal charge. Chlorine starts out with 7 valence electrons. Each chlorine gets one of the ones that it contributed to the bond. And I see 1, 2, 3, 4, 5, 6 non-bonding around it. Each chlorine has a formal charge of 0. How about the phosphorus? Phosphorus starts out with 5 valence electrons. If you got a periodic table, look it over. Phosphorus has 5 valence electrons. It gets half of each of the bonds, which gets it 1, 2, 3. And in terms of the non-bonding, another 2. So for phosphorus, 5 minus 3 minus 2, it ends up having a value of 0 as well. Really good check here. All zeros, this is a really strong Lewis structure. Consistent with the octet rule, really strong Lewis structure. Formal charges add up to the charge on the entire molecule. I like to see that too. So I'm really confident that this is the best Lewis structure. How about this one? So HCN. So within this case, we're going to put these together. I first asked to ask, well, what's going to be my central atom? Well, I guess before that, I got to add up the number of electrons. So hydrogen has 1, carbon has 4, nitrogen has 5. I'm just looking at the periodic table to see how many valence electrons there are. I get a total of 10. I'm going to put carbon as the central atom. I don't want to put hydrogen because it can only form 1 bond. Carbon can form the most bonds and it's the least electronegative here. So I'm going to draw my initial sketch. I've got a total of 10 electrons that I have to account for. Right now, I'm only accounting for 2 in this bond and 2 in this bond. Next step, let's complete octets around the nitrogen. Hydrogen, I don't have to do anything with. So at this point, I've got a total of 10 electrons shown. Hydrogen is fine. Nitrogen is fine. Carbon, I got some work to do though. That's nowhere near an octet. I've only see a total of 4 electrons around it. I want to get to 8. Where will those electrons come from? I'm going to shift the ones from nitrogen and I'm going to increase the bond order there. I'm going to shift the electrons in and turn that into a triple bond. Does this work now for the octet rule? Hydrogen, it can only form a single bond, so that's all set. Let's look at the carbon. 2, 4, 6, 8 works for carbon. How about the nitrogen? 2, 4, 6, 8 works for the nitrogen. I want to do my usual plan here. Let's check the formal charges on this. Each of the hydrogens has a formal charge, or the hydrogen has a formal charge of 0. 1 valence electron, it gets half of the bond, formal charge of 0. How about the carbon? 1, 2, 3, 4 contributions from the bonding. No non-bonding, gets a value of 0 overall. Nitrogen starts out with 5 valence electrons. It has 1, 2, 3 coming from the bonding. It has a lone pair left over. 5 minus 3 minus 2, formal charge of 0. Sweet. That's looking great too. I think we've ended up with a great Lewis structure. It's consistent with the octet rule. Formal charges are 0 throughout. We're moving ahead. We're enjoying daylight saving time. Everything's looking sweet. This one, as far as when do we begin to care about formal charges? Well, look at this example right here. Let's say we're trying to draw the Lewis structure for CO2. If we're looking at this example right here, if we followed our plan as we went through, both of these are plausible. And when I say both of these are plausible, these are both completely consistent with the octet rule. Each of the oxygen atoms has 8 around it. The carbon has 8 around it. One case, it has 2 double bonds, and in the other case, a single and a triple bond. So if I'm using the octet rule to say which one is better, they're the same. So I'm going to consider, well, does the formal charge tell me which one is better? If I'm evaluating the formal charges for the CO2 molecule here on the left, I think that the oxygen atom on the left, on the far left, has 6 valence electrons. It has 2 electrons that were being found in the bond, a total of 4 that was non-bonding. So for each of those oxygen atoms, 6 minus 2 minus 4 gets me to a value of 0. How about for the central carbon? It's also leading to a value of 0. So I really like the Lewis structure here on the left because everything is 0. Take a second, see if you can assign the formal charges for the one on the right. See how those come out. Let's see how we could use that to evaluate the two. So I've worked through a couple examples. See if you can apply that same reasoning. See if you can now fill in the bottom portion and calculate the formal charges in this molecule on the right.
Dr. Clark, can I ask a question about the formal charge?
Yeah.
So for the half of the bonding atoms or electrons, sorry, could you, that describes the number of electrons contributed by that atom to the bond, correct? It's not half.
The way that you can, and I like the way that they're sort of showing it within this box picture. What they're saying within here is when we're counting the bonding ones, you're right when you're sort of envisioning how many did that atom contribute. What we're really just saying is, okay, like within this double bond, there's a total of 1, 2, 3, 4 electrons. Let's just say they're exactly shared. 2 of them are going on one side and 2 of them are going the other. So with formal charge, we're just conceptualizing saying, oh, what if we just divide them up that way? And that will make it so we don't double count in any of the electrons. We're just going to divide up. What I mentally do is I really think like that, like, oh, here's a bond. Let me draw a line between that and see how many electrons that would now give me on each side.
Okay, perfect. Thank you.
Yep. And that was a really good question. That's why they say this 1/2 the bonding. They're just saying divide up the bond that way. When I look within this one on the set right here, on the right-hand side, those are my values. So for carbon is again a value of 0. It has the same number of bonds, even though it was a single and a triple as 2 doubles. So for carbon, it still ends up being 0. But notice what happened to the oxygen. This one on the far left right here ends up with a formal charge of -1. The one on the far right, a formal charge of +1. So one thought is, okay, I think I did it right because look, If I add those all together, it should add up to 0, and it does. So seeing that it adds up to the overall charge, that to me is a pretty useful check that I drew a plausible structure. But this is not as likely. If I can have them all zeros, that's much more likely to be the correct Lewis structure than ones where I have +1s and -1s. So this is an instance where I'm using the formal charge as a criterion to say, is this the correct Lewis structure or not? This would be the better one because they're all zeros. Now, I've mentioned a couple times, well, what happens if we're using formal charges and they add up to the overall charge, like for an ion? Let me work through now an example of how do we do this if we have an anion. I think all of the ones that I had in the pre-class video were all neutral. Let's see how this one works. So the molecule includes nitrogen, carbon, sulfur, and it's got a -1 charge on it. So I need to first of all figure out how many valence electrons do I have. So what I'm going to do is I'm going to add up and get to the total. I got 5 coming from the nitrogen. I'm just looking at the column that it's in. There was 4 coming from the carbon, 6 coming from the sulfur, and I'm adding 1 more to the total because it's a -1 charge. If you ask, well, where does that additional 1 come from? I don't know. It's within this polyatomic right here. I've got to increase the number of valence electrons because it's an anion, so I added 1 more on there. So now within this polyatomic anion, I need to have a total of 16 valence electrons in my resulting picture. This would be my initial sketch that I have. I'm putting the least electronegative. Carbon is great in the center because it can form a lot of bonds. So this would be my initial sketch. Right now, I've got 2 in this single bond, 2 in this single bond. I have to add up to a total of 16. So I'm going to follow just the normal procedure. Let's complete octets around the outside. This is how I'm going to show that. I've added a new feature for us. I put these brackets and I gave a minus sign. This is the notation we use when we have ions. We put brackets around them and then we put what the charge is on the outside. So right now, if I were to look at this total thing, 2, 4, 6, 8, 10, 12, 14, 16. Okay, I've accounted for all of the electrons, but I don't have octets there on the center one. So I'm going to have to shift electrons and begin to account for, to help out the central atom, because I know my central atom is going to be consistent with the octet rule. Now, I gave that a try, and I found that there's different ways that I can make it work. All 3 of these options right here, they are all consistent with the octet rule. I could have a triple bond between the carbon and sulfur, double bond, triple bond between nitrogen and carbon. These are all using 16 electrons. These are all using the octet rule. How do I know which one's best? I got to use a formal charge. This is a great example of which of these is the best Lewis structure. It comes down to which one is consistent with our guidelines for the formal charges. Now, I've shown a couple examples within that. These are the resulting formal charges. So I did the math exactly the same way that I worked on the other examples. If I were to assign these each, right, number of valence electrons minus half the bonding minus the number of non-bonding, these values in red, these are the resulting values that I got. So first of all, do they add up to the total charge? -2, 0, +1, that adds up to -1. Excellent. I think that was done correctly. -1, 0, 0. That adds up to -1. I think it was done correctly. 0, 0, -1. Yep. Notice in each of these cases, the formal charges, they add up to the overall charge of the -1 anion. Next thought, though, is, okay, which one of these is best? What were our guidelines for using formal charges? First thing is we want to have them as close to 0 as we can. So I'm going to get rid of this one. I don't think that one is close to 0. -2, 0, +1. I much rather have these that are closer to 0. I think we're getting closer to our answer now. Next thought though, which of these is better? I need to have a negative somewhere because I know that it's an anion. It's got to end up having a -1 somewhere if the overall thing is -1. Then we're to the next thought. Okay, if I have to have a minus somewhere, I'm going to put it on the more electronegative. Nitrogen, that's one of my most electronegative. Remember our plan? Most electronegative was fluorine. The next tier were immediately to the left and immediately down below it. This would be the best one within that set right here. This particular assessment right here, what I think I just did was I looked at the formal charges that were on the different atoms, and I applied the guidelines to say, okay, which of these now is going to give me the best Lewis structure? Sometimes you'll see it called the most dominant Lewis structure. And in order to evaluate that, I had to say, I want it to be all zeros if I can. And if I can't, I'm going to put the negative on the more electronegative. Really typical exam question there as far as applying the formal charge. Here's another anion, okay? So I know I'm working through a lot of different ones, but I'm trying to illustrate different features. So this is a anion with carbon, nitrogen, and it's got a -1 charge on it. So first thought, same plan as usual. How many valence electrons? Carbon has 4, nitrogen has 5. I add 1 more because it's a -1 anion. That gets me a total of 10. Give this a try, okay? See where this one takes you. See what happens if you start to now construct a Lewis structure, Lewis symbol for this. Try to put it together. I'll share my work in just a second. See if you can follow the plan. We don't have to worry about the central atom. We're just going to try to see if we can get to octets. I'm going to give you about 2 or 3 minutes on this. I want you to try to give it a good try. Okay? See if you can take this one through and try to make sense of it. Okay, so here's my work for this. Okay, so my first step is let's draw a single bond between the two of them. Next step is we need a total of 10 valence electrons. So let's 2, 4, 6, 8, 10. This would be a total of 10 valence electrons. Now, when I start to put them around here, I'm not liking that picture right there at all for octets. If I put on 2, 4 on each side as lone pairs, I'm not getting octets for the carbon or the nitrogen. If I shift them in though and make a triple bond between the two of them, okay, this now does work. This does work for octets. The carbon on the left has 2, 4, 6, 8. The one on the right, 2, 4, 6, 8. Notice we're putting brackets around it and the minus sign because it's a -1 anion. This is working here for octets. Above it, I show what the formal charges are. The formal charge for the carbon here is -1. It has 4 valence electrons, -3 being contributions from the bonds, -2 from the lone pair. So the carbon ends up being -1, the oxygen ends up being 0. The reason I'm picking this example right here is it seems like we can't make both of our rules work. Both of our criteria can't be satisfied. And by that, I mean, this is great for the octet rule, but I've put the more negative charge on the least electronegative. It's not consistent with the formal charges. So which of these makes sense? Which rule wins? The way I want you to think about it, for those atoms that always form octets, carbon, nitrogen, oxygen, fluorine, the octet rule is absolutely going to be the one that we work with. If it's not perfect in terms of formal charge, so be it. If we get stuck like this and we say, well, what do we choose? Octet rule or formal charge? For carbon, nitrogen, oxygen, and fluorine, the octet rule is going to be our absolute go-to for that. These are octets I see. I don't like it in terms of formal charge, but the octet rule is going to win for these atoms. For carbon, nitrogen, oxygen, fluorine, we're always going to be using the octet rule. Now, within our last set, we've covered a lot of different ideas within this grouping. Okay, when it comes to doing the formal for doing our Lewis structures. When I say we've done a lot of different ones within the video, I thought people had a really good job of being able to begin to understand the idea. The questions that people were adding to that were, well, how do you begin to handle it if it's an ion or not? How do I begin to think about what the central atom is? Really good questions. And that's what I was trying to pick up within tonight's class. These examples that I list right here of trying to draw Lewis structures, I think you're now in a really good shape to be able to give these a try. These are giving you some clues as far as what the central atom is going to be, okay? I highly recommend seeing if you can improve your skill with Lewis structures before our next class. Lewis structures, as far as how we're going to use them, in some ways they're as important as stoichiometry was back in chapter 3. We're going to use Lewis structures throughout chapter 8, and we're going to use it in probably half of chapter 9. So I really need you to try to get comfortable and gain some skill and fluency with these. As soon as you can, the better. And it's something that we're also going to be practicing within our next class. Okay, a lot of ideas we covered. Are we hanging around if you got questions? We're going to pick up and finish chapter 8 next time and move a little bit into chapter 9 as well.
For the C or the Cn minus anion.
Yep.
How did you know to evenly distribute the electrons, like the unpaired, or sorry, the lone electron pairs between carbon and nitrogen?
Are you thinking in terms of this bottom image here?
Or no, like the second step you did where you had 4 on each side. Why didn't
Yeah,
you put,
good question. I put it there. You could have just as easily put them all on one side. But I think my point is that as long as you have a single bond, you weren't going to make it work for the octet rule. That preliminary step right there, I completely get if you would have said, oh, wait, I'm going to make it all octets on one side and then see what I'm left with. Whatever you did in that middle step, I think you would have gotten to the same conclusion, which is I got to start making double and then triple bond.
Okay. When they're in a covalent bond, is it not ever going to be that there's unpaired electrons?
You can have unpaired electrons and still have a covalent bond. I'm thinking something like well, like just Cl2 or F2, right? Those would be where we have a single bond between both of them, and we do have unpaired electrons on the atoms themselves. Same thing would be like in O2, right? I'd have a double bond between those, but I'd have unpaired electrons on the oxygen. Or are you thinking unpaired electrons in a different way than that?
I just mean like on the Lewis structure where you just have one electron on the left without another, like they're not in pairs, is what.
Oh, okay, got it. So you mean like an electron, just a single electron where it's not paired up? Yeah, that has a name. That's called a free radical. Those right there, if you have an unpaired electron all by itself, as you might imagine, they're very reactive. They're going to combine with other things quite readily. So free radicals, they do exist, but they're very short-lived. They're parts of chemistry, atmospheric chemistry. I think even in biology, free radicals exist, but they don't exist for very long. So in order to be stable, we almost always are going to see them where they're paired up instead of independent unpaired electrons.
Okay, so if we're drawing a Lewis structure for a molecule, we should just always have them paired up.
Yeah, I don't think you'll ever have examples where you have unpaired ones. The only time you'll have an example is if the molecule has just an odd number of electrons, because then you don't really have a choice.
Okay.
This is kind of just a clarification on the cyanide ion as well. So you said that we don't love the formal charges, but isn't that kind of how it has to be, since the whole compound has a charge? It has to add, the formal charge has to add up to the charge.
I agree. I'm sure within this, I have to have a negative somewhere. If I have to have a negative on carbon or nitrogen, I'd rather put it on nitrogen because it's more electronegative, but I can't make that work with the octet rule.
Okay, and then obviously for our exam, we won't be drawing anything, but would a possible question on an exam be asking which resonance structure is preferred?
Yeah, real good question. So how Lewis structures then show up on tests, the kinds of things that we can do. Sometimes we'll have questions that are multiple choice. So it'll show you different Lewis structures and it'll ask you, okay, which of these is the appropriate one? So somewhat times we give you ones and we ask you to say, okay, pick the best one. Another thing that we can do is we can say, okay, draw it and then tell me about it. Meaning, draw the Lewis structure. Okay, tell me how many lone pairs there are. Draw the Lewis structure. How many double bonds do you have? Draw the Lewis structure. What is the formal charge on the nitrogen? So that's the other thing that we do. We can say, draw it and then tell me about it. And so what you're getting at when you mention like resonance, that's an idea we'll get next time. That's another sort of, okay, do some analysis and then now tell me about it. And that's why I think Lewis structures are really an important skill, because a lot of those next questions of tell me about it, do some analysis, they begin by first having the Lewis structure.
Okay, thank you.
Mm-hmm.
I have a question about the example right before this one with the NCS anion.
Mm-hmm.
So when looking at the periodic table and the electronegativity trends, it looks like nitrogen and sulfur are both equally distant from fluorine.
Yep.
Like they're both 2 steps away from fluorine. So how did you know that nitrogen was more electronegative?
I'm with you. Real good question. So within this one right here, I grabbed this figure from a different book. I like it because the way they've color coded it, they show fluorine is the most, and then it shows the second tier, the second most electronegative are those immediately to the left and immediately down below.
Okay.
You know, notice, because I'm completely with you. It sure seems like, well, wait, sulfur's right there too, right? How do you know? So I really like the way this one's color coded. So it makes me place the sulfur one properly.
Okay, awesome. Thank you.
Good question.
If the anion has a charge of like -2, do we want to distribute the negative charge like across both the different atoms, or do we want to keep them all on the most electronegative?
Yeah, I would say It would be probably preferred if I could have like a -1 and another -1.
Mhm.
I think that would be getting me better of saying that's closer to having all zeros.
Yeah.
So yeah, I would be saying a -1 is better than a -2.
Okay, and then we talked about like the difference between ionic bonding and non-polar covalent and polar covalent. Is this definition of an ionic bond, is it going to capture different molecules than is just the definition of a metal and a non-metal, or are they basically all the same like compounds?
Well, good question. So within that, you noticed within that that simulation there, it put it on a continuum, right?
Mhm.
It was more and more up my ionic, more and more covalent. It didn't say, okay, after you get over this line, you're ionic. It put it on a continuum there. And so the official answer is even an ionic bond, it's a little bit covalent. It's not always entirely just the cation and the anion. It's not always entirely just +1, -1. There's always some degree of sharing. In our picture, we just want to say, okay, we've got a +1 and -1. But the real answer is you never have entirely just +1 and -1. There's always some degree of covalency there, some degree of sharing.
Okay, and so do the compounds that we usually talk about as ionic with metals and nonmetals, are those always going to have a higher electronegativity difference than the ones we usually talk about as just covalent? Or no?
Yeah, oh yeah, good. Yeah, so I would say that the electronegativity difference when we end up saying here's a metal and a non-metal, really big difference on that. When we're looking at the ones and we're saying this is polar covalent, they're much more similar. If I'm looking just with the data that I have here, like the electronegativity for something like sodium chloride, I see a sodium value of 0.9, chloride 3. That's a much larger difference than if I'm looking at combinations here amongst my non-metals. So polar covalent, there's a difference, an ionic, an even greater difference.
Okay.
I have a question about the cyanide ion question.
Mhm.
So for molecules that have carbon, nitrogen, oxygen, and fluorine, should we just always assume that like our Lewis structure is okay based on the octet rule? Like, should we not calculate?
Yeah, really good question. So I would say the key thing that I would be evaluating on that, it would be the octet rule. I'd make sure that it's working for that. Personally, within my own setup is when it comes to calculating the formal charges, I can do it pretty quick. You know, I mean, it's the same plan. I can do it pretty quick. I almost always calculate the formal charge for that just to make sure that I did it right. Meaning, oh, it's got to end up being -1 because it's -1. Because the kind of error I might make, I might not add up the number of valence electrons right at the start. You know, maybe I would forget to call it an anion, something like that. That's the mistake I usually make. Or if I'm drawing, maybe I forget to account for them properly. So I find that that formal charge calculation at the end, it's just a real quick check to me. Oh, did I do it right? Because it adds up to be the overall charge. But I agree with you. That wouldn't be something that I would be then using as an important variable to try to evaluate it, because I know for those, the octet is going to be all I need.
Okay, makes sense. Thank you.
Yep.
Do we want to say something like carbon dioxide has a dipole moment, or is it only for molecules with 2 atoms?
A really good question. So right now, the way that we first introduced it, we're talking about a bond dipole. We're looking at electronegativity differences between the 2 atoms that are contributing to the bond. The very next thing that we're going to do is, after we learn about the geometry at the start of chapter 9, we're going to talk about the dipole for the entire molecule, whether based on the symmetry, is it a polar molecule or not. So the examples that I was looking at that I brought up, like F2, HF, LIF. I was very intentional. I was just making those where there were only 2 atoms in the molecule. Chapter 9, we're going to increase in a cool way, and we're going to look at what the actual structure looks like and consider the entire molecule when it's just not paired up like that.
Okay.